Now we are going to move to the paper titled Performance Evaluation of Quantum Secure Symmetric Key Agreement, which is authored by Amin Royce, Muhammad Ikram, Macquarie University, and Muhammad Ali Kafar, Macquarie University, and Optus, Macquarie University Cybersecurity Hub. So, are you hearing me, Royce?
Hi, yes, Amin.
Yeah, welcome, Amin. And can you share the screen, please?
I send a request to share the screen.
Yeah. Soft reminding, you have 20 minutes to present your paper. After that, 2 minutes for question. So please go ahead.
Hello, everyone. Can you see my screen?
Yeah, we can see it, but you need to enlargen it a little.
Yeah.
Okay, it's all good now. I can start then. Good afternoon, everyone. My name is Amin. I'm going to present my work as Master of Research student at Macquarie University. The title is Performance Evaluation of Quantum Secure Symmetric Key Agreement. So I will divide the presentation in 4 parts. I will explain the introduction and motivation and the experiment setup, and then I will share the key findings in our experiment in 3 different parts. And next, the problem that we want to solve is that how do we prepare our system against post-quantum attack that we know we will attack the current classical public key cryptography. It will affect all our communication infrastructure globally, so we need to find some solution for the key agreement. And several options already exist, that is the software-based like post-quantum algorithm. However, they will take larger resource and take longer to standardize. And there's a growing concern that the security are not yet long time tested, which has now triggered hybrid deployment trend. Another option is using quantum key distribution, which is a hardware solution based on the quantum photon. This will be harder to scale and will need expensive quantum hardware. So a better option is to develop a symmetric agreement which will use symmetric key encryption by the end of the key agreement. And we can use post-quantum or hybrid encryption at the beginning of the key agreement. And we will show this in detail later. So this is an illustration of quantum computing attacks. For this to become a reality, we will need 2000 qubits implementing Shor's algorithm. However, attacker can start harvesting our traffic and decrypt that later, and they can store that starting now. So with this formula from Mosca, we need to minimize X, minimize the quantum safe deployment time before the quantum computing set will capable of breaking our public cryptography in polynomial time will exist. So this is an urgent matter. Next, we have explored this related works. There has been some work that benchmarking the post-quantum TLS and SSH with simulated network condition or real-world ones, and we have explored that there's a hybrid deployment trend by the top technology companies. So, for example, Apple has combined a post-quantum algorithm and classical algorithm inside their iMessage platform. So recently, Arkit developed a symmetric key agreement platform where they start the key agreement by wrapping random secrets in different post-quantum algorithm, and then later on derive a symmetric key which has been proven to be quantum secure, to be used later as the session key and communication key between, for example, Alice and Bob. However, their solution is a proprietary solution. We don't know about the details of this. So in this work, we develop an open implementation of this symmetric key agreement ideas using open source and accessible components. So similarly, user will authenticate first to the key server, and then we define the 4-part secrets that will be encrypted in hybrid, so 2 parts encrypted in post-quantum and 2 other parts in the classical elliptic curve. This will be sent to the key server and to be used to derive the symmetric key that will later be used for communication. So symmetric key will be very lightweight. So we reduce the resource that needs to be used if we always use a post-quantum algorithm. So for benchmarking purpose, we will also have classic SKA, which will only use classic algorithm, and quantum SKA that will only use quantum algorithm in the step 2. Next, this is our experiment setup. We use Cosmion, an open source key management server that is configured as the key server to facilitate the key management, such as the key generation, encryption and decryption, and so on. And we will use a Linux network emulation features to simulate various network conditions, such as to introduce bandwidth variation, latency, and delays and packet loss. And we also use Argon as the key derivation function, and we also use Shannon entropy calculator to measure the entropy of the generated keys for security evaluation. So we run every scenario 30 times and collect the time using GNU time in Ubuntu. Next, we have the experiment result of the first part, which is the simulated network settings. So in default condition, which is the 4 giga bandwidth on our Amazon server with 0 delay and packet loss, there's a very little overhead. So quantum will be faster. However, hybrid with a little bit more overhead will give you more guarantee of security, combining the classical and the quantum. And then we introduce network delay to the communication between client and server. So this to simulate the geographical distance. We can see that the overhead are still consistent. And also we tested with the introducing packet loss to simulate network quality. The overhead are also consistent. And then we also introduce variation in the bandwidth because not everyone will have 4 gigabytes bandwidth on their network. And this still show the consistent overhead. And we look closer at the sub-process operation. We can conclude that the key generation process contribute more in the performance difference than the encrypt and decrypt operation, which are similar between the SKA types. Then for the second part of the experiment result, we will look at the multi-user setting or the scalability measurement. So we can see here using 4 CPU, the overhead is only 1 second per 5 concurrent users. So we add users that doing SKA process at the same time. And then we also measure the percentage in performance increase by adding the CPU from 2 to 4 using the virtual machine specification. So we can see that the performance increase is between 50 to 60%. So this is very scalable solution. And then we also confirm that the sub-process that contribute higher in the different performance is the key generation process. The encrypt and decrypt operation are similar between SK types. So if we want to optimize this, we need to be faster at the key generation. And the last part of the experiment result is the security evaluation using entropy measurement, where we measure the entropy of the generated cryptographic materials. So we can see here, for example, for the entropy of initial private keys, the post-quantum algorithms show higher entropy than those keys generated by classical algorithm, and they maintain consistent and sufficient randomness with the entropy values approaching the maximum possible value for 256 bits. And this is very similar for the other cryptographic materials. And so in summary, we presented an open implementation of hybrid and quantum secure SKA as a solution for key exchange protocol that is capable of withstanding quantum attacks while remaining lightweight and robust in various network conditions and also highly scalable. The second is that our findings that post-quantum algorithm produce higher entropy values in the cryptographic materials. This information can be used by attackers to differentiate encrypted traffic, and it can help attackers in choosing the classical encrypted traffic for harvest no and decrypt ledger attack. And then the last one is that since this is an open implementation, these schemes can be customized. Like you can use different encryption that you prefer at different key size. You can add hardware security module. You can increase the parameter of key derivation function. You can use different key management software, or you can also increase the parameter of the secret sharing parts at the beginning of the key agreement. And the last thing, we will release the bash scripts automation at the GitHub later. Thank you, and I can answer any questions you have.
Yes, thanks, Amin. We are open the floor for questions. Looks like there is no question. Many thanks, Amin, for your great